Hello, ladies and gents. Today I would like to investigate the integral, which I'm going to call I of AB, which equals the integral from 0 to 1, x to the b minus x to the a over natural log of x dx, where 0 is less than or equal to a is less than or equal to b. And that would imply that I of AB is convergent. For instance, using L'Hopital's rule on the integrand, as x approaches 1 from below, we would find that the integrand approaches b minus a. And of course, at 0, the integrand would simply approach 0 for x approaching 0 plus. All right, well, first of all, let's see if we can evaluate this. Okay, consider this double integral. I'm going to call this double integral star so we can refer to it later. And it's the integral from 0 to 1 of the integral from a to b of x to the s ds dx. And this is easily done. This equals the integral from 0 to 1, x to the s over the log of x from a to b dx. And evaluating that at those limits will equal the integral from 0 to 1 of x to the b minus x to the a over the log of x dx, which is, of course, our integral we want to evaluate, I of AB. Now, using Fubini's theorem, we can exchange the order of integration of what I call star. And this implies I of AB equals, after we exchange that order, a to b of the integral from 0 to 1 of x to the s dx ds. And this equals the integral from a to b of integrating that inner part. We'll get x to the s plus 1 over s plus 1 from 0 to 1 ds. And that equals the integral from a to b of 1 over s plus 1 ds, which is easily done. This, of course, equals the log of s plus 1 from a to b. Notice there's no need for absolute value signs here because s plus 1 is going to be greater than 0. And, of course, this equals the log of b plus 1 minus the log of a plus 1. Now, I began to think about, well, what would be the integral if in the integrand we, instead of the integrand, what about the integrand squared or cubed or to the 4th power or any nth power? Could we come up with a formula for that? Well, evidently, we can use the same technique here of coming up with a multiple integral and exchanging the order of integration. And I'm going to call, in general, I sub n of AB equals the integral from 0 to 1 of x to the b minus x to the a all to the nth power over the log of x to the nth power dx. And of course, the restrictions on a of b would be 0 is less than or equal to a is less than or equal to b, where n is any natural number. We can see that a and b have to be greater than or equal to 0. Otherwise, we'll have an x in the denominator here and an x in the denominator here. And of course, at 0, that would cause a problem. Okay, now consider this multiple integral. I'm going to call this star star. And that is the integral from 0 to 1, the integral from a to b, integral from a to b, dot, 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 integral from a to b of x to the s1 times x to the s2, dot, 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 times x to the s sub n, ds1, ds2, dot, 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 dsn, and then finally dx. And here the integral signs from a to b, there are n of them, of course. Okay, we can observe that the inner integrals are separable. And when we do those integrations, this will equal the integral from 0 to 1 of x to the b minus x to the a over log x times x to the b minus x to the a over log x times times x to the b minus x to the a over log x dx, which of course equals the integral from 0 to 1 quantity x to the b minus x to the a all to the n divided by log of x to the n dx. And of course this is our target integral, in of ab, right here. This is what we want to evaluate. Now, again, exchanging the order of integration as we did in the first part of our video in star star, we'll transfer the dx integral to be done first. So we're going to have I sub n of ab equals integral a to b, integral a to b, integral a to b, integral 0 to 1 of x to the, multiplying all those x's out, we have x to the s1 plus s2 plus plus sn dx, then ds1, ds2, all the way to dsn. And, of course, this will equal the integral a to b, a to b, 1 over s1 plus s2 plus plus sn plus 1, ds1, ds2, dsn. Now, the goal would be to find, is there a closed form for in of ab? Well, I think there is. Let's see if we can do it. Let's introduce a new variable, s, and make sure it's greater than or equal to 0. And I want us to consider I sub n of a plus s over n, comma, b plus s over n, which, according to the definition of in, is going to be equal to the integral from a plus s over n to b plus s over n, the integral of a plus s over n to b plus s over n of 1 divided by s1 plus s2 plus plus sn plus 1 ds1 dsn. Now for each k between 1 and n, let's let u sub k equals s sub k minus s over n. These are just going to be our u substitutions for each s sub k. Of course, this the du sub k will equal ds sub k in each case. Okay, now let's continue with the integral. That'll make I sub n of a plus s over n, b plus s over n equal to, now these are going to be, when we plug in these new limits, it'll be the integral a to b, integral a to b of 1 over u1 plus u2 plus plus un plus s plus 1 du1 du2 dun. Well, you might ask, where does that s come from? Well, for each one of these sk's, we have to plug in a uk plus an s over n, and there are n of them. And s over n times is going to leave us with our s in the denominator. Okay, this implies that I sub n plus 1 AB, remember I sub n plus 1 is just the same thing as in, only with n plus 1 variables. So if we simply integrate this right here from a to b, ds, we have u1 through un, there's n, and then an s, that's n plus 1 variables. So if we just integrate in of a plus s over n, b plus s over n ds from a to b, this will give us in plus 1 of ab. We'll call this star, star, star. So in other words, so far, we actually have in plus 1 in terms of some in here. Now, we claim that I sub n of ab is going to equal this closed formula. 1 over n minus 1 factorial. The sum as k goes from 0 to n of n choose k minus 1 to the k times n minus k quantity times b plus k times a plus 1 all to the n minus 1 power times the natural log of n minus k quantity times b plus k times a plus 1. And this is true for all 0 is less than or equal to a is less than or equal to b, and for all n natural numbers. Okay, first we need the following lemma. The lemma states, let Rn of a, b, y equal the sum as k goes from 0 to n of n choose k times minus 1 to the k times the quantity n minus k times b plus k a plus y all to the n minus 1. Now, we claim that Rn of a, b, y equals 0 for all 0 less than or equal to a, less than or equal to b, and for y greater than 0, and for n a natural number. Okay, here goes the proof. We're going to do it by induction on n. Our base case will have n equals 1. So R sub 1 of a, b, y equals the sum as k goes from 0 to 1 of 1 choose k times minus 1 to the k times quantity 1 minus k quantity times b plus k times a plus y to the 1 minus 1. And here you'll notice in parentheses, this quantity is always greater than 0. And so then we don't have to worry about a 0 to the 0 issue. We won't have to deal with that. Simply because y is greater than 0, and the rest of this can only be, the minimum the rest of this can be is 0. And of course, this sums out to 1 minus 1, which equals 0. So this is our base case. Now, our inductive hypothesis. Let's assume Rn of a, b, y equals 0 for all 0 less than or equal to a, less than or equal to b, and for y greater than 0. Let's suppose that is true for some n greater than or equal to 1. Okay. R sub n plus 1 of a, b, y then equals the sum as k goes from 0 to n plus 1 of n plus 1 choose k times minus 1 to the k times quantity n plus 1 minus k all times b plus ka plus y to the n. Okay, now let's take the partial of our n plus 1 with respect to a. Doing that, we get n times the sum as k goes from 1 to n plus 1 of n plus 1 choose k times minus 1 to the k times quantity n plus 1 minus k all times b plus k times a plus y to the n minus 1, taking the derivative with respect to a. And you notice this k here that comes from the chain rule? that allows us to start the sum from k equals 1 instead of the original k equals 0. Now, let's notice that n plus 1 choose k times k equals n plus 1 times n factorial over k factorial n plus 1 minus k factorial times k. This equals n plus 1 times n factorial over k minus 1 factorial times n minus the quantity k minus 1 factorial. Simply because the k and the k factorial, the k and the k in the k factorial divide out, leaving us with a k minus 1 factorial in the denominator. And this equals n plus 1 times n choose k minus 1. So this implies the partial of r n plus 1 with respect to a equals n times n plus 1 times the sum as k goes from 1 to n plus 1 of n choose k minus 1 times minus 1 to the k times the quantity n minus the quantity k minus 1 all times b plus ka plus y to the n minus 1. Now, let's re-index k to k plus 1. This yields minus n times n plus 1 times the sum as k goes from 0 to n of n choose k times minus 1 to the k times the quantity n minus k all times b plus k plus 1 all times a plus y to the n minus 1. Notice the minus sign out here comes from the minus 1 to the k plus 1. That would normally be right there. Okay, this equals minus n times n plus 1 times the sum as k goes from 0 to n of n choose k minus 1 to the k times the quantity n minus k times b plus k times a plus y plus a all to the n minus 1. Notice I took the a out of this term and moved it over here with the y. And this equals minus n times n plus 1 times r sub n of a, b, y plus a. And by hypothesis, this equals 0. Recalling that y plus a only has to be greater than 0. And since y is greater than 0 and a is greater than or equal to 0, y plus a is greater than 0. Therefore, the partial of r n plus 1 with respect to a of a, b, y equals 0. This implies integrating both sides with respect to a. This implies Rn plus 1 of a, b, y equals some function g of b and y. And the important thing to note here is that g is independent of a. Okay, in a very similar manner, taking the partial of Rn plus 1 with respect to b will give us n times the sum as k goes from 0 to n of n plus 1 choose k minus 1 to the k times n plus 1 minus k times the quantity n plus 1 minus k all times b plus ka plus y all to the n minus 1. And of course, the n plus 1 minus k comes with the chain rule. The n out here comes from the exponent rule. Okay, now, again, let's simplify n plus 1 choose k times n plus 1 minus k. This equals n plus 1 factorial over k factorial, n plus 1 minus k factorial times n plus 1 minus k. which equals n plus 1 times n factorial over k factorial n minus k factorial, where clearly the n plus 1 minus k and the n plus 1 minus k in the n plus 1 minus k factorial in the denominator cancel each other. And so this equals n plus 1 times n choose k. Well, this implies that the partial of r n plus 1 with respect to b equals n times n plus 1 times the sum as k goes from 0 to n of n choose k minus 1 to the k quantity n minus k all times b plus ka plus y plus b all to the n minus 1. And here again, notice we took the 1 times b from this term and transferred it over here and combined it with the y term. Well, this simply is n times n plus 1 r sub n of a, b, y plus b, which equals 0 by hypothesis. Again, y plus b, the only restriction on that is that it's greater than 0, which it is since y is greater than 0 and b is greater than or equal to 0. Therefore, the partial of g with respect to b and y, the partial of g of by with respect to b, of course, is equal to the partial of rn plus 1 with respect to b of a, b, y equals 0. Well, this implies that rn plus 1 of a, b, y which equals, of course, g of by must be a constant c. So the important thing to note here that g is independent of a and b now. So we can pick out any a and b to find our constant c. Well, the easiest one to do is a and b both 0. So this implies c equals rn plus 1 of 0, 0, y, which equals the sum as k goes from 0 to n plus 1 of n plus 1 choose k minus 1 to the k y to the n. That's simply plugging in a is 0 and b equals 0 into our definition of rn plus 1. And this, of course, by the binomial expansion, equals y to the n times the quantity 1 minus 1 to the n plus 1, which, of course, is 0. Therefore, rn plus 1 of a, b, y equals 0 for all 0 is less than or equal to a, is less than or equal to b, and y is greater than 0. Therefore, finally, by induction, rn of a, b, y equals 0 for all 0 is less than or equal to a, is less than or equal to b, for all y greater than 0, and for all n natural numbers. Now to the main result. Let f sub n of a, b equal 1 over n minus 1 factorial. The sum as k goes from 0 to n of n choose k times minus 1 to the k times quantity n minus k all times b plus k times a plus 1 to the n minus 1 times the log of n minus k all times b plus ka plus 1. We claim that I sub n of ab equals f sub n of ab for all 0 less than or equal to a, less than or equal to b, and for all n natural numbers. And we recall that I sub n of ab is our target integral. So let's start with the proof. We proceed by induction on n once again. Our base case will be n equals 1. f1 of ab then equals 1 over 1 minus 1 factorial. The sum as k goes from 0 to 1, minus 1 to the k times 1 minus k all times b plus k times a plus 1 to the 1 minus 1 times the log of 1 minus k all times b plus ka plus 1, which equals the log of b plus 1 minus the log of a plus 1. And we recall that this is indeed I1 of AB. Okay, our inductive hypothesis. Assume I sub n of AB equals f sub n of AB for some n greater than or equal to 1, and for all 0 is less than or equal to a is less than or equal to b. By star 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 from earlier, I sub n plus 1 of AB equals the integral from a to b I sub n of a plus s over n, b plus s over n ds, which equals the integral from a to b of f sub n of a plus s over n, b plus s over n ds by our hypothesis. Which equals the integral from a to b of 1 over n minus 1 factorial. The sum as k goes from 0 to n of n choose k minus 1 to the k, quantity n minus k, all times the quantity b plus s over n, plus k, times quantity a plus s over n, plus 1, all to the n minus 1, times the log of, once again, n minus k times b plus s over n, plus k times a plus s over n plus 1 ds. Now this equals the integral from a to b of 1 over n minus 1 factorial. The sum as k goes from 0 to n of n choose k minus 1 to the k times the quantity n minus k times b plus s plus ka plus 1, all to the n minus 1, times the log of n minus k times b plus s plus ka plus 1 ds. And that comes just simply from simplifying these terms here. This equals 1 over n minus 1 factorial, bring that on the outside, times the sum k goes from 0 to n of n choose k minus 1 to the k times the entire quantity 1 over n times the quantity n minus k times b plus s plus ka plus 1 n to the n rather times the log of the quantity n minus k times b plus s plus ka plus 1 minus 1 over n squared times quantity n minus k times b plus s plus ka plus 1 all to the n, and we take s from a to b. This is just integrating this right here with respect to s. If you take the derivative of this, you'll see you'll get back that. All right, this equals 1 over n factorial times the sum k goes from 0 to n choose k minus 1 to the k, times quantity n plus 1 minus k times b plus ka plus 1 all to the n times the log of quantity n plus 1 minus k times b plus ka plus 1. That's inserting b into the first term, minus quantity n minus k times b plus k plus 1 times a plus 1 all to the n times log of quantity n minus k times b plus k plus 1 times a plus 1. And that comes from inserting a into the first term up here. Now, for the second term, we have plus minus 1 over n minus 1 factorial n squared times the sum as k goes from 0 to n of n choose k minus 1 to the k times the quantity n plus 1 minus k times b plus ka plus 1 all to the n, that's inserting b into the second term, minus quantity n minus k times b plus k plus 1 times a plus 1 all to the n. That comes from inserting a into the second term. And we're going to define these two blocks as a plus b. Now let's first look at b. b is the second term here. I'm outlining with the arrow. Let's re-index the second term in b. So this term right here, we're going to re-index that. We're going to change k into k minus 1. And this will yield b equals minus 1 over n minus 1 factorial n squared times quantity is the sum as k goes from 0 to n of n choose k minus 1 to the k times the quantity n plus 1 minus k times b plus ka plus 1 all to the n. That term doesn't change. Minus, now, the new sum as k goes from 1 to n plus 1 of n choose k minus 1 minus 1 to the k minus 1 times the quantity n plus 1 minus k times b plus ka plus 1 all to the n. Okay, what does this equal to? It equals to, again, minus 1 over n minus 1 factorial n squared on the outside times the quantity. Here's the k equals 0 term, this first term would be the quantity n plus 1 b plus 1 all to the n, plus the sum as k goes from 1 to n of n choose k minus 1 to the k, quantity n plus 1 minus k times b plus ka plus 1 all to the n minus n choose k minus 1 times minus 1 to the k minus 1 times quantity n plus 1 minus k times b plus ka plus 1 all to the n minus, which is going to be the k equals n plus 1 term, minus 1 to the n times the quantity n plus 1 a plus 1 all to the n. Now, let's simplify n choose k minus 1 to the k minus n choose k minus 1 to the k minus 1. That's this part minus this part, as you'll notice that they have this factor in common. Okay, well, this pulling out the minus 1 to the k minus 1, we get that times what's left over, minus n factorial over k factorial n minus k factorial minus n factorial over k minus 1 factorial n plus 1 minus k factorial. Simplifying, this is minus 1 to the k, taking out the n factorial over k minus 1 factorial n minus k factorial, that times what's left is 1 over k plus 1 over n plus 1 minus k, which equals minus 1 to the k, n factorial over k minus 1 factorial, n minus k factorial. Combining these two terms leaves n plus 1 over k times n plus 1 minus k. Combining all this brings us to minus 1 to the k, n plus 1 factorial over k factorial, n plus 1 minus k factorial, which finally, of course, equals minus 1 to the k, n plus 1 choose k, Well, this implies that b equals minus 1 over n minus 1 factorial n squared times the quantity, again, n plus 1b plus 1 all to the n, that's the k equals 0 term, plus the simplified center term, the sum k goes from 1 to n of now n plus 1 choose k minus 1 to the k, quantity n plus 1 minus k times b plus ka plus 1 to the n, plus the n plus 1 term, which is minus 1 to the n plus 1, times the quantity n plus 1a plus 1 all to the n. This can be written compactly as minus 1 over n minus 1 factorial n squared times the sum as k goes from 0 to n plus 1 of n plus 1 choose k minus 1 to the k times the quantity n plus 1 minus k times b plus ka plus 1 all to the n, which equals 0 by our lemma. So in other words, b equals 0. So what's left? So that means I sub n plus 1 ab equals a. Finally, let's look at a. Let's rewrite a here. So we recall that a equals 1 over n factorial. The sum as k goes from 0 to n of minus 1 to the k, n choose k, quantity n plus 1 minus k times b plus ka plus 1 all to the n times the log of quantity n plus 1 minus k times b plus ka plus 1 minus quantity n minus k times b plus k plus 1 times a plus 1 all to the n times the log of quantity n minus k times b plus k plus 1 times a plus 1. Now again, re-indexing the second term, k to k minus 1, just as before, gives a equals 1 over n factorial times the quantity, the sum, k goes from 0 to n of minus 1 to the k, n choose k, times the quantity n plus 1 minus k times b plus ka plus 1 all to the n log of quantity n plus 1 minus k times b plus ka plus 1 minus our new re-index term, the sum as k goes from 1 to n plus 1 of minus 1 to the k minus 1, n choose k minus 1 times the quantity n plus 1 minus k times b plus ka plus 1 all to the n times the log of quantity n plus 1 minus k times b plus ka plus 1. Which equals 1 over n factorial times the quantity n plus 1 times b plus 1 to the n times the log of n plus 1 times b plus 1, that'll be our k equals 0 term again, plus our center terms, the sum as k goes from 1 to n of minus 1 to the k, n choose k minus 1 to the k minus 1, n choose k minus 1, all times the quantity n plus 1 minus k times b plus ka plus 1 all to the n times the log of quantity n plus 1 minus k times b plus ka plus 1 plus, this will be our k equals n plus 1 term, minus 1 to the n plus 1 times the quantity n plus 1 times a plus 1 all to the n times the log of quantity n plus 1 times a plus 1. Again, just as in earlier, we combine the minus 1 to the k n choose k minus 1 to the k minus 1 n choose k minus 1. We get 1 over n factorial times the quantity n plus 1 times b plus 1 all to the n times the log of quantity n plus 1 times b plus 1 plus the sum as k goes from 1 to n of minus 1 to the k, n plus 1 choose k, times the quantity n plus 1 minus k times b plus ka plus 1 all to the n, times the log of n plus 1 minus k times b plus ka plus 1 plus minus 1 to the n plus 1 times the quantity n plus 1a plus 1 all to the n times the log of n plus 1 times a plus 1. And of course this first term is our k equals 0 term. These are the center terms, k from 1 to n. And this term here is our k equals n plus 1 term. And this can be written very concisely as 1 over n factorial times the sum as k now goes from 0 to n plus 1 times minus 1 to the k, n plus 1 choose k, times the quantity n plus 1 minus k times b plus ka plus 1 all to the n times the log of n plus 1 minus k times b plus ka plus 1. And of course, this simply equals f sub n plus 1 of ab. Therefore, I n sub 1 of ab equals f of n sub n plus 1 of ab. For all 0 is less than or equal to a is less than or equal to b. Therefore, finally, by induction, I sub n of ab equals f sub n of ab. For all 0 is less than or equal to a is less than or equal to b, and for all n in the natural numbers. And this completes our proof, and this completes our video. Thank you so much for watching.